Welcome everyone. In today's class, we are going to discuss about various digital circuit optimization techniques. Specifically in today's class, I am going to talk about briefly about the optimizations, retiming, replication, folding, clock gating and glitch minimization. So, these are the optimizations. It's not is the exhaustive, but they are very common in most of the commercial EDA tools. Okay. So, I will just talk about the optimizations and their impact in general in circuits. So, if you look into this optimization in a EDA circuits, EDA tools, specifically they try to optimize either area, power or timing. Timing in the sense either latency or throughput or the clock period, right. So, it can be various optimizations. So, let us start with this retiming, and before going to that let us see how we represent the circuit. So, circuit in general represent as a net list. Okay. So, net list is something is basically you can think about a graph where it is basically a graph where there are set of inputs, there are set of outputs, and inside the net list what you have? You have basically the gates, you have registers and some interconnection units, right. So, basically those gates and registers can be considered as the nodes, and their data flow among them or the interconnection among them can be considered as edge, right, and that is how we usually represent the circuit. Okay. So, usually this net list is a very common terminology in context of this circuit representations or optimizations we talked about. Okay. So, as I mentioned, you can have this AND gates, OR gates and so on. You might have some flip flop, right. So, and there are interconnections. So, we can represent just like this, right. So, then this might come back to here and so on. So, this is a feedback loop and so on, right. So, this is how we can represent the circuits. So, let us talk about retiming. Okay. So, and it is primarily used for timing optimizations or try to improve the clock period. Okay. So, I want to run the circuit in faster clocks. Okay. So, let us try to understand that. So, for that let us take this kind of a simple graph, right. So, suppose this is the graph and these are the green nodes are basically combinational unit, they can be AND gate, they can be OR gate, they can be add, they can be anything, right. So, multiply and so on, right, XOR and so on. So, these are the gates, and what how this clock period is determined? The clock period is determined the maximum combinational path length, right. So, that means it is the path between two sequential elements or the path from input to some sequential elements or path from a sequential element to the outputs. Okay. So, basically it is a the path consists of only combinational units, right. So, there is no sequential element involved in a combinational path. Okay. And how this determine the clock period? Because say this is 10 nanoseconds, say this is 15 nanosecond, this is 15 nanosecond and this is a 30 nanoseconds. Okay. So, the total delay is basically 30, 60, 70 nanoseconds, right. So, if this is the longest path, I am say so if you just assume, so this is say 5, this is say 25. Okay. So, the longest path here you have to understand that this is 1, this is the longest path, right. So, it involves actually all the nodes. So, what would be the total delay of this node? You can actually understand the delay of the all nodes basically here, right. So, which is basically plus 30, which is basically 100 nanosecond, right. So, you remember here that there are many paths, this is the longest path which determine the clock period, but there is another path like this, right. This is one path which is 70 nanosecond, this is another path, right. This is another path, there are many paths actually here. So, among all the combinational paths, the path that has maximum delay or the time when time to execute that particular path is determine the clock period. Why? Because your clock should be longer enough, right. So, this clock period should be longer enough to execute that path, combinational path, right. You have to complete this execution of this whole combinational things within the clock period, because whenever the next positive edge clock comes, by that time your data should be ready at this point, right? Otherwise, the circuit will be unstable, right? It will be not in a stable state. So, if I take this particular circuit, and since I found that the longest path, combinational path, is basically of 100 nanosecond, so my clock period should be at least 100 nanosecond, right, which is basically 10 megahertz, right. Basically, it is 1 by 100 nanosecond, so which is basically is 100 megahertz, right. This is the clock speed. So, so your clock, so this circuit won't run more than 10 megahertz clock, right. So, you might do some kind of combinational optimizations here, but it is not able to reduce the circuit, optimized circuit at after a certain level, right. So, after certain level, combinational optimizations whatever I talked about in previous 2 classes may not be applicable here, right, or may not able to optimize this combinational circuit further. Okay. So, in that case the retiming comes into picture. Okay. So, what retiming does? It is try to move the register or the sequential element of the design such a way that it does not change the functionality of the design, it does not change the latency of the design, but it actually reduce the combinational path length. Okay. So, I will just give you an example. So, suppose, so in this particular path here, what is the latency? The latency is basically 2, right, because there are 2 registers involved. So, whatever input you are going to give here, after 2 clocks your output will be ready, right. But I can see that there is a longest path is basically very long, which is basically of 100 nanosecond, right. So, what we can do here, I will just clean the circuit little bit, say this is 15, this is 15, this is 30, right. So, I can see here that, so this is basically 30 plus 45, 50, 70. So, this is the path is actually is very long, right. So, if I can put the registers at this place, right. So, instead of this register, so I just do not have this register, say if this register place is here, right. So, basically I then actually split the paths into 2 kind of, right. So, this path length is 10 plus 5, 15 plus 20, 40, and this path is 15 plus 30, 45, right. So, basically I can actually split the combinational path by half, right. So, I can see here that it will not go beyond 50 basically, right. So, it is kind of, I can say this is basically 30 plus 40 or this is 40, 55 basically, right. So, my clock period can be now 55 nanosecond, right, it is almost double, right. So, this is what, and if I just move this register to this place, you can see for any path from input to output, my latency will remain 2. Although earlier I have only 2 registers, I have now 4 registers. So, the number of register actually does not determine the latency, rather the latency determined by the number of registers in any path, right. So, the maximum number of registers, that is the latency. So, here I can clearly see that if I just remove this register and place it here, my latency will remain 2, but my clock period almost become double, right. So, this is what retiming does. So, retiming what it does, it is basically as a optimization method, which basically can take the complete circuit and then it actually model it such a way that I am not going into the how this retiming is implemented. This is very interesting approach. But what it does is basically you give a certain target clock period, say I say my target clock period is 60 nanosecond. So, what it does, it try to model the problem such a way that once this retiming is done, it actually places this register here, because if it places there the target clock period, so it can achieve the clock period 55 nanoseconds, which is which means the target clock, right. So, the retiming is a optimization which basically moves the register in a circuit such a way that given a target clock period it can achieve that, right. So, you can understand that combinational optimize sometimes has a limitation, because it is just between 2 registers and you may not able to do everything, right. So, retiming is very useful optimization and it is actually implemented in all EDA tools, which basically does this. Okay. So, there are 3 types of retiming, I would say. The first one is the global retiming, where you actually take the complete circuit and you model it and you give a target clock period, and then it will actually achieve that particular clock period. and if it is not, it will say ki I am not able to reach this. Say suppose for example, if you try to achieve here 40 nanosecond, probably with 2 register it might be difficult. Actually it is possible, because you can move this register backward, this register forward, and somehow you can manage it, right. So, if your target clock period is not achievable, then it will say it is not possible to achieve that, but if it is possible, it will actually give you the retimed circuit or the modified circuit, where the circuit functionality remains same, latency remains same, but it achieves the target clock period. This is the first one. The second one is called local retiming. Sometimes this, because this circuit might have million number of gates, and retiming usually kind of order of n cube algorithm. So, that may be too complex to apply to a complete circuit, but I can always find out a small part of the circuit where it is actually it is causing problem, and then I can actually apply the retiming locally also, right. So, you can actually kind of divide and conquer kind of approach also you can apply, that you can actually take step by step part of the circuit to and then apply retiming there. So, that is the local retiming, and the third one is called the peripheral retiming. Okay. So, the peripheral retiming is also interesting, that sometime you can understand that this combinational optimization cannot apply across registers, right. There may be some combinational circuit here, this part, then there may be some registers here, and then there will be again set of combinational circuits, right. So, so basically what I am trying, so there will be some combinational circuit here, then you have a set of registers, then again some combinational circuit, and then set of registers, right. So, when you try to apply this combinational circuit, I mean optimizations, you have to take this each combinational block separately, right. You have to optimize this, you have to optimize this, you have to optimize this separately or individually, right, because you cannot do this optimization across register, because the behavior functionality is have a boundary, right. This performance of this combinational circuit has a boundary, this registers. Okay. So, what the periphery retiming does is basically moves all the registers at the periphery, or either to the input side or output side, right. And then the whole combinational circuit can be considered together, and then I can apply more optimizations, and then once it is optimized, I can actually retime back this register to intermediate place, so that I can reach the target, right. So, this periphery retiming does two things. It first allows to apply this combination optimization for a larger circuit, because otherwise it is actually have a boundary of registers, right. I cannot apply the complete circuit, but if I just apply peripheral retiming, my registers will be moved to the outside. So, basically what I am trying to say is that you move this register here, you move this register here, and this is out there. So, now I have, there is no register here, there is no register here, this is a complete circuit which is a combinational unit. So, I can apply the combinational unit in this particular part, right, and I can do the more optimization apply, because there are more opportunity will come because of the bigger circuit, and then you move back this register using the retiming algorithm in proper place, so that your target clock is met. Okay. So, these are the three kind of techniques, and these are all done to timing minimization. Okay. So, now I just talked about that this registers have to be moved, right, but what is the rule, right. So, how to make sure that when move the register, the function will remain the same. Okay. So, for that the basic idea is that whenever there is a node here, if you try to move the registers, the register must present in all input. Okay. Suppose you want to move this way, okay, this direction. So, that means you can only move the register only if it is available in all the inputs, and once you move, you should move them to all outputs, right. So, this is the retime circuit. So, for example, if you have a gate like this, and if you have a register here, you cannot move it here, right, because there is no register at this part, right. So, this is then you cannot you cannot apply retiming here, right. Similarly, if you have say 2 register at the input, you want to move into output, what you are going to do, you have to put them in all outputs, right, not only one of the output, then only the functionality remains same, right. So, this is what the retiming, right, I can move this to the outside, and similarly if I try to move them back, I can actually, if it is in all output side, I can move them back to into input, but if say this register is not present here in this particular output, then I cannot move them into outside. So, that will change the functionality. Okay. So, this is what this retiming, and I have an example here which I already kind of explained. So, now I just try to see that how I can apply these rules here. So, suppose I want to move this register, as I mentioned, I have to, if I move, it is only one input. So, I can move it, but I have to move it into two output place, right. So, this is what is done here, and then say suppose I want to move it further. So, if I try to move it further, this one, what will happen? So, this is a single input to this node. So, I have to move it to both places, right. So, I can move it into both places, right. So, this will not be there now anymore, this is not there, right. This is a straight line connection. And now for this node there are two input is both have register. Now, I can move this both to output port, right. So, if your objective, so the example I have taken, that say suppose I found that moving this register to this place is important, is something needed, right. So, to do that, first I will do this step. So, it will come here. Now, I cannot apply, I cannot move this register here, because there is no register here. So, what I have to do, even if I have to move it here, I have to move, although this move may not be necessary, because probably say this path is not so critical path. So, this register is not may not be needed, it is not necessary, but because I need to move this register here, first what I am going to do, I am going to move this register to these two places, and then I can take these two register and move to these places, and this is the resultant circuit, right. This is what this retiming does. So, the way it is done, it actually follows the retiming rules. Okay. So, the retiming can also be used for reducing the number of register as well, because if your objective is not to, so if the circuit is very small, say it does not matter whether, so basically kind of all computational path are actually meeting the target clock, but I want to reduce the number of register. So, that is also possible, because in that case what is basically happen. So, number of register I can move and I can actually reduce the register, and the basic rule is that suppose there is a high fan out, right, and if there is a 3 registers here. So, the latency of the circuit is 1, because from the input to output side all path has 1 registers, right. Whereas, if I just move it to in the input side, right. So, this is a correct one, because all output fan out has register. So, I can move this way, and still this is the resultant circuit has still the latency 1, but this circuit is basically better, because in terms of number of register, because here I need 3 registers, here I need 1 register, but the functionality of the both the circuit same. So, I can actually utilize retiming to reduce the register, minimizing the number of register as well, right. So, for example, I have given an example here, say suppose I have this case. So, I can actually take these 2, I can move it here. So, then 1 register will reduce, then I can take these 2 and I can move it here, right. So, this is what is done here. So, here I have 6 register, here I have 4 register, but both the circuit actually same. Okay. So, this is again can be done using retiming. Okay. One more application is basically optimal pipelining, right. So, suppose I want to create a pipeline design. So, I know this is my circuit, and then this circuit is basically has to be pipeline. That means, you have to add register layer, right. So, you have to add pipeline stages, and pipeline stages is nothing but a kind of set of registers in that particular path, right. And say these are the delays, right, 10, 13, 6, these are the register delays. So, I can put the registers at the input, and then I can set a target clock, right. So, I can set a target clock, say 20 nanosecond, and then I can ask the retiming, I can apply retiming. So, retiming automatically add this pipeline in proper places, right. So, it will do it one set of register, it will place here, it will take one set of register, place here, and it is basically you can understand that this is not a single step. Basically, first it will take this register, it will place here the way I mentioned, then it will take, it will bring it here, then it will take these 2, it will bring it here, then it will take this, it cannot move it now. Then what is going to do? So, these registers are not there. So, the 2 registers are like this now. So, this register will also come here, because once you try to move it here. So, now these 2 registers are there. So, I can move it to here, right. So, this is the one set of register movement, right. So, after moving one set of register, it will look like this, and it is not there. Then it will take these registers and it can move here and here, then it will can take this and it will move it here, right. This is how it can does, right. So, this will result in this circuit. So, this is one pipeline stage, this is one pipeline stage, and the delay will be determined by max of these 3 delays, right. This is how this pipelining can also be implemented using registers, right. So, these are the many applications of retiming. So, that is why this retiming is so important algorithm, and it is actually available in all kind of EDA tools. Okay. So, let us now move on. So, another important optimization is called replication. So, it is very simple, but very useful optimization. Okay. So, it is primarily used for routing congestion, I mean reducing the routing congestions and delay, right. So, combinational delay or routing delay rather. Okay. And also it is basically it actually helps in reducing the total wire length. Okay. So, let me try to give the example what is the replication. So, suppose there is a node here which is very high fan out, right. So, it has say 1000 fan out. Okay. So, there are so many 1000 fan out. Okay. So, that means this signals is going to 1000 other nodes. Okay. Now, think about the scenario that now I am going to do the routing and I am going to create the chip. Think about this FPGA or say ASIC. So, once I am going to place this node somewhere, right. So, suppose this is your area of the chip. Okay. So, since it's 1000, it is going to 1000 different locations, this it has 1000 fan out. So, my objective will be to put this 1000 other nodes near to this place, so that the wire length will be reduced, right. But it is not possible because there are I mean I cannot put so many things nearby places. So, what I can be done? So, there may be some nodes will be placed here, some will be placed very far, right, because you cannot place all in together, right. So, other nodes will be in very far. So, this three may be nearby, this may be nearby, this may be nearby, but this may be here and so on, right. You can understand that. So, now what is going to happen? You can understand here that it actually creates very long wire, right. So, then when you do the routing, you have to route this particular wire in through the routing area, right. So, basically you can understand clearly that it actually increase the routing length will be more, and also the congestion will be, you have more pressure on the routing algorithm, because you have so many long path, you have to schedule them or can route them, and also the delay of the path will be more, right. So, if the path, this particular wire length is more, obviously the signal reach from this place will be, it will take more time than it is reaching from here to here, right. So, these are the so many things will come because of a high fan out node. Okay. So, what I can do now as a solution is this, right. So, what I am going to do, I have the source node, I will just say place it here, and what I can do, instead of creating so many long wire, I will replicate the source and I will create some buffer node, right. So, what I am going to do, I am going to create say another 3 source node buffer, right. So, I just connect them, right. So, whoever is nearby, it is okay, and then whoever is long, I mean, and then I try to place the other nodes near to this source, right. So, then the wire length will be less, you can understand, right. So, I am going to place them here, then I am going to place them here. So, it is basically I replicate my source into multiple copy. Earlier all such wire is long, right. So, all such wires are long. Now, I only few long wire, right. So, these are the 3 few wire, and because the other node, these are the nodes will be placed to near to this source, these are the node source, I mean nodes will be placed to this source and so on, right. So, this is what it does. So, earlier say if there are say 700 long wire, it is 700 x wire. Now, I only say 3 source nodes. So, it is basically 3 x long node and then this plus this. So, this will be always less than this. So, and so basically this is a very simple optimization, the replication. So, I am going to replicate a high fan out node, and as a result it will help me to reduce the total wire length. Is very much clear that I do not have many long wires, I have only very few long wires, and other nodes which will be nearby to that source. As a result, total wire length will be reduced. My delay will be less because since this path is coming here. So, after that this delay will be lesser than the longer wire length, and the third is basically since the number of long wire is less. So, routing congestion will also get minimized. Okay. So, that is the idea of replication. It is very simple, but very powerful optimization, okay, to do so many advantages. So, the question here is that I understand that I have to. So, basically I will create this high fan out node multiple copies, right. I am going to create buffer for that, but how to distribute this node, right. How do I know that I have to place this node near to this, which are the nodes I am going to put to this source, which are the nodes I am going to put under this source, which are the nodes I am going to put under this source, and so on, right. So, this is something is a question, and basically we can actually keep track of the hierarchy, and the nodes within a hierarchy I can close together, right. I can break them together. So, the idea is that if you have a, this is a high fan out source node, and there are so this is going to say there are 100 connections here, 100 connections here, 100 connections here, but I know this is another module, this is another module, and this is another module. So, when I am going to split them, I am going to split them into module was, right. So, what I did, I just, this is my source node, and now I created multiple source, 3 copy of the source, and I just put whatever it is here, I am going to put it near to this, whatever the fan outs are here, I am going to put to this source, and whatever the fan outs are here, I am going to put it here, right. So, this will help to keep the nodes which is basically strongly connected kind of, right. So, whenever they are inside the module, they are kind of strongly connected, and if I place them together, so placing them during routing or placement and routing, it will be easier. Okay. So, that is the basic idea of replication. Okay. So, let us move on. The next one is another interesting and very important optimization is called folding. Okay. So, this primarily used to optimize the area. So, what is this? Basically, if you found in your data path or in your circuit that there are many repetitive kind of instances, right. For I just taken an example here that I found there are 4 instances of 2 add in series. Okay. So, it is basically kind of 4 copies of the same circuit, right, which is circuit is basically 2 adder. So, what this folding does? It fold this 4 into 1. Okay. So, I am not in the modified circuit, I do not anymore have 4 copies of these 2 adders, rather I have only 1 copy of the adder. Okay. And then what I am going to do? I am going to multiplex these inputs to this 2 adders, right. So, you can see here this guy is doing A plus B. So, I am going to put say this is not 2 adder, multiply and add. So, this is basically same thing. So, it does not matter what is inside. So, it is basically multiply and add. So, I can see here that I can put this for this multiplication what is happening. So, it is basically A, I can put this A, C, E and G into this mux, because this is the left input to the multiplier, and the right input is basically B, D, F and H, right. So, B, D, F and H I can put into another multiplexer, and I can multiplex this input to this multiplier, right. So, I can have a 2-bit signal now. So, S1 S0, S1 S0. So, if it is basically 0 0, then say A into B is going to happen. If it is 0 1, then C into D is going to happen. If it is 1 0, then E into F is going to happen, and if it is 1 1, then G into H is going to happen. And similarly, after that this is multiplying with this x1, x2, x3, 4. So, I am going to put another marks here. So, that this will now going to when it is basically again this is S1 S0. So, effectively when this is S1 and it is 0 0, is basically this circuit will be executed. Once it is 0 1, this circuit will be executed. When it is 1 0, this circuit will be executed, and this is 1 1, then this circuit is going to execute, right. So, this is what is folding. So, basically what I am doing here is basically time division multiplexing, right. I am going to use it the circuit for 1 copy of the circuit, and I am going to multiplex the input, but it is a time division. So, because 1 copy of the circuit cannot perform 4 operations at the same clock. So, I have to distribute in 4 clocks, right. So, earlier this circuit was working in 1 clock, right, because they are all parallel. This will take 4 clocks, right, because it is basically time division multiplexing is happening here. Okay. So, I will come back to that. And so, if this is for parallel copies, right, if the operations are in series, I want to fold them, that is also possible. So, what is I am going to here do is that I want to fold these 2 adder into 1, right. So, I can create that, and then what I can do, I can put B here, A here, because I just put into 2 multi. So, this is say S and this is also S. So, in the first clock when it is 0, so it will going to do bx plus ax, right. So, this is going to happen. In the next clock when s equal to 1, I want to perform the result of this ax plus bx with cx, right. So, what I am going to do, I am going to give cx here. So, the next clock when s equal to 1, cx will come here and I need a plus b, which is computed in the previous clock. Because it is calculated in the previous clock, so I need to store in some register, right. So, that is why I put a register here and then I put a feedback loop here, right. So, this is my actually ax plus bx, right. So, in the when is s equal to 1, then it is actually calculate this ax plus bx plus cx. This is what is going to happen, right. So, that means in clock 1 a 0 plus b 0 is going to happen. So, x is something the clock. Next clock a 0 plus 0 plus c 0 is going to happen. In the third clock a 1 plus b 1 is going to happen, right. This is how I can actually alternate or time division multiplexer things. So, again you can understand that this circuit is going to work, right. Only thing is that earlier it was taking 1 clock to execute this, now it is taking 2 clocks, right. Earlier it is 1 clock, now it is 2 clocks, right. So, this is what is folding transformation. So, the EDA tools usually identify such instances and try to fold them. Okay. But one thing is something the question might arise to you, that what about this, how I am going to manage this 1 clock versus 2 clock, right. Because you can see here that this is probably, so this is say one module, right, and this input is coming from another module, right. So, earlier it was giving in every clock, right, and similarly this output is going to say some other module, right. So, and this modules has to be synchronized, because in your initial specification, if you think about this is the module implementation. So, if I implement this by this here, so this module is going to give you the input in every clock, right, and in next clock the corresponding output will go to this module, right. This is how the synchronization happen, right, or handshaking happen. They know that this is that every clock I am going to get the next input, and this module also know every clock this module will give me the correct output. But now in the modified or the folded circuit, I can see here that this is actually now taking 2 clocks. So, it actually changes the kind of that interfacing. It also create the problem to the interface, because now this you have to do some kind of things here also, right. So, you have to make this circuit wait for two cycle to get the every get the output and input in every 2 clock cycle. Similarly, for this case the corresponding output circuit has to wait 4 cycle to get the output, right. So, that means something has to be changed here. So, which is something very complex, and we should avoid that, right. To do that, what I can do, I can run this module now. Say if it is a 2 clock, I can actually run in 2x clock. This is a normal clock, 1x clock. So, suppose this is running in 100 megahertz, this is earlier all modules was running in 100 megahertz, now I am going to run it in 200 megahertz, right. I am assuming this circuit is replaced by this folded circuit, and this is also running in 100 megahertz. What is going to happen? Now, it is basically it is giving the input in 100 megahertz speed, and when the next clock come, because this is a 200 megahertz, its 2 clock of this circuit will be done, right. So, that means it will actually can produce the output, and for this circuit or this circuit, because they are running in 100 megahertz and this is running in double speed, they are going to get this output in every clock, right. So, that means whenever I fold a circuit or the module, that I have to run the circuit in that folding factors more speed, right. So, that the interface will be unchanged, right. So, they do not understand whether this circuit was running in 100, I mean for them it is still running kind of 100 megahertz, because earlier also they are sending the input in every clock. In the modified circuit also they are giving, they should able to give the input or the output to this module in every clock, because this circuit is running faster speed. So, when one clock of this circuit means 2 clocks of this circuit. So, it's basically the interface will be remain unchanged, right. So, when you do the folding transformations, what usually we do, we basically identify that common pattern, and then you fold factor, identify the kind of folding factor, how many copies are there, you basically create the folding circuit and then run the folded circuit in n into clock speed. So, that the interface is remain unaltered. Okay. So, that is the idea. Okay. And usually for DSP applications, the folding is something very useful, because in DSP there are many such repeated state instances. Okay. So, this is about the folding transformations, and it primarily used to reduce the area of the circuit. Okay. So, the next one I am going to talk about is clock gating, which is basically used for dynamic power reduction. Okay. So, the basic concept of clock gating is very simple. Okay. In a circuit you have two kind of power, right. So, static power and dynamic power, and dynamic power in very high level, it is basically toggling of the it comes because the toggling of the bit, right. So, when you your some signal goes from 1 to 0 or 0 to 1, the power consumption is more compared to if it is remain from 1 to 1 or 0 to 0 in the next flow, right. So, when you toggle the signals in your circuit, usually the power consumption increases. Okay. So, now if you identify, so a circuit, a part of the circuit, which you can understand that for say this circuit is running for ever, right. I can know that from say 11 cycle to 25 cycle, this circuit is not doing anything useful, right. So, it is basically kind of the output it produces basically remain unused. Okay. So, what I can do is, but since the clock is coming, the input registers getting modified, and every time you get a new data. So, there is a high chance that your some signals get toggle, and as a result to this combinational input you have getting a different output. So, right, there is a toggle, and as a result this circuit also consuming more power, right. What I can do, I can just get the clock, right. So, I can have a clock enable. So, this is my clock signal. What I can do here, I can actually have some controller which will generate this enable signal 0 for say the example I am giving, that 11 to 25, that particular cycle it will give you 0. As a result your clock will remain 0, right. As a result, what is going to happen, your content of this register will not change, because you do not get any positive clock, right. As a result, whatever the previous data it will contain, this register will contain the same register, same data, right. So, that means I am actually stopping the toggling. So, earlier if it is whatever the value, in the next clock also the same value, no toggle. So, the power consumption of this part of the circuit will be less, and whenever I want to activate this, I will just put clock 11 equal to 1. So, that this circuit will work as it is, right. So, this is basically the very high level concept of clock gating. Is basically if you identify that a particular part of the circuit which is basically not happening, which basically useful for a large amount of time of the complete execution time. So, I can just use the a clock enable, basically disable the clock for that part of the circuit for the time when it is basically idle. Okay. And we should have a controller which is basically generate this control enable signal. Again, this is very simple, but very powerful technique for reducing dynamic power in a circuit. Okay. So, the last one that I am going to talk about is a glitch. Okay. So, let us try to understand what is glitch. Glitch is basically a hazard, right, or undesired transition, okay, in a circuit. So, let me just give the example of glitch, how the glitch is generated. It basically generate when for a gate two input is not coming at the same time, right. So, it is just some minor timing difference between these two input, and that then it will create some glitch at the output. Okay. So, let me example with this some small example. Suppose your x was coming here and suddenly it become 1, right. So, then this 1 will come here, and say since there is a gate here, let us say the NOT gate, there is a NOT gate. So, now earlier this was 0. So, that is why the NOT gate output is 1, and suddenly it become 1. So, it will be 0, but it will reach earlier than this one, because it will take some amount of time to make it 1 to 0, right. So, this is the timing change, right. So, when it is become 1, it should be 0, but at this moment this become 1, and at this moment it becomes 0. So, this is the period of time when this signal will remain 1, right. So, this is 1 and this is also 1. As a result, output will be AND gate will be 1, right, because it is a 1 and 0, the output of the AND gate will be always 0, right, because I am giving x and x bar to AND gate. But because for a very fraction of time the both input remain 1. So, I am going to get a glitch here, right. So, my remain will be like this, right. Whenever I change this value of x 2 1 to 0, I will always get a kind of glitch, right. So, this is something is not changing the functionality of the circuit, but it is actually the glitch means some power, right. Whenever you have a glitch, some power consumption going to happen, right. This is kind of a toggling of the value, right. So, this is obviously if you have a NAND gate you will not feel this glitch, but if you think about there is a AND gate which input is coming directly and there is a big combinational unit here which is giving the output and the second input, the same input is going to this big combinational unit and then it is coming to this input. So, obviously, there will be some delay, there will be some delay for this compared to this. As a result, there will be some glitch going to happen. Right. So, glitch is something happen because of the signal if both the signal does not come for a particular gate at the same time, right. So, that is something reduce, I mean it is a kind of undesired behavior and this unnecessary consume some power, right. So, for that usually what we do is basically do similar kind of transformations. The first so for control intensive design, if there is a say input say suppose there is a mux here, okay. So, what is going to happen? So, there is a mux here and so say suppose this is your select signal and there is a glitch here, right. So, suppose this is 0 and 1. So, actual signal is 0, but suddenly it become 1. So, it was say suppose this is also 0 and this is 1 actually. What is going to happen? Because it suddenly become 1, you will get a small 1 at the point and then it will be 0, right. So, again it will create a glitch. So, the point here is that if there is a glitch in the control signal, that actually get propagated into data path, because of the glitch the wrong input will be selected for a transit very fraction of time and as a result that might create some glitch, okay. So, for control signal if there is a glitch that gets propagated to the data path, and for data path when you have chaining of arithmetic unit, right, then also it actually creates some kind of glitch, because you can think about that if there is a adder here and its input coming from a adder and a multiplier, right. Obviously, this will come first, this will come bit late, because it is basically suppose their actually input is same, right. So, obviously, there will be some delay here, as a result there will be glitch at the output of the this output of this adder, right. So, because of the both cases you have can actually glitch, and there are similar kind of optimization can be done to make sure that this glitch actually can be reduced further, right. So, basically one is basically integrated clock gating to reduce the control signal hazard or the control glitch. You can actually clock the control signal, so that you do not have any this glitch will be minimized, because this control signal only be 1 when the clock comes, right. You can actually to handle this basically you can restructure the multiplexer network, or you can actually choose alternate data path. Basically, you restructure data path so that you have uneven delay for both the inputs, right. So, these are the kind of techniques is getting applied to reduce the glitch, right, and again it is targeting to reduce the power consumption of the circuit. Okay. So, with this I conclude today's class. Again I just try to emphasize that I have taken very few optimizations is very important and is very well known and very popular in all EDA tools. There may be many more optimizations and there may be context specific optimizations which we should learn in detail, but in the scope of this particular course I just talk about very few very important optimizations and their impact in digital circuit. Okay. Thank you.